Thank you. So before we get to today's talk, we have one scheduled for next month, Interannual Variability in Eddying North Atlantic Ocean, Quintin Jame from Florida State University. But following that, March, April, we do not have anything scheduled. So if anybody's got something, it's only a 15-minute talk. It only needs to be broadly relevant to our task team goals. So you can send an email to Kristen or myself if you're not sure, or just step up and volunteer with something. Today's talk is from Yochanan Kushnir from Lamont, and he's going to talk about North Atlantic Ocean response to atmospheric forcing with and without ocean dynamics.
Okay, thank you very much, Mike. So you already described the title or read the title of my talk. This is collaborative work here at Lamont between myself, Ming-Fang Ting, Kwihua Lee, and Donna Lee. A small team that is all interested in ocean interaction with the atmosphere. And I should emphasize this is really preliminary, and I think it's just a teaser for things that can be done more with this subject in the future. So the general motivation for this is described by this slide from Clement et al., who showed that you can get a pattern that looks very much like an AMO and Atlantic multi-decadal oscillation or Atlantic multi-decadal variability that also has a very similar spectral properties if you look at observations at a coupled ocean model and at a model that is coupled, the models that are coupled to a slab ocean that has no dynamics. So the question is, does this really mean that this is the same, that the same mechanisms operate behind those two patterns? So we thought about a very simple approach to try to show no, that it's not the same, and that if you look at the lagged behavior or time behavior of these patterns, you can see a difference between the ocean behavior in the two situations, in the coupled to full ocean and coupled to a mixed layer. And this reminds a lot of the early work that was done on this subject way back in the I think early 2000s or late 1990s, and I'll get to that at the end. So first of all, just a quick look, and if you look at the three panels on the left, so we are taking here a single model, which is the NCAR CESM. It was run for a very long control run, pre-industrial control run, without any external forcing, and we look at the SST. We look at here in this case the subpolar gyre sea surface temperatures, being that the subpolar gyre is the focus of all the interaction that leads maybe to ocean atmosphere coupling. So the left panel shows year by year variations for the first I think it's 600 years of the integration. The integration itself is 1800 years long. And you can see that if you low pass filter it, you see the interannual variability. If you low pass filter it, you see ups and downs on a lower frequency, which you could argue remind you of low frequency behavior of the observations. I'll explain the right panels in a minute, but I just wanted to show you first what happens when you look at the slab ocean. In a very quick looking at this, you can say, okay, the slab ocean behaves in terms of the time behavior about the same as the full GCM, but I'll show you in a minute that the actually time scale of the slab variability in the subpolar gyre is slightly higher frequency than, or slightly or more or less, depending on how you define slightly, than in the fully coupled model. So now I'm going back. The right panels are. I'm using here a trick that I used in the paper in 1994 when I started looking at this, and I'm doing a 15-year running difference so I take 15 years and I look at the difference between the average over 15 years and the previous 15 years, and I scale everything by the noise in the data, by the variance of the data, to create some sort of like a t variable. So anytime this function peaks above a value of 2 or a little over 2, then it's 99% significant shift or change that happens. And 15 years is used here arbitrarily because it's not necessarily clear from the onset that this is the time scale that's appropriate for the model, but we'll see that it does give results that are quite answering some of the questions that we asked. So anytime this peaks up, there is a positive transition from cold to warm, and anytime there is a negative peak, there is a transition in the data, a low frequency transition from a warm to a cold phase. And again, here, if you compare just quickly the slab ocean to the fully coupled ocean, you see almost a similar behavior. But let's look further into this. First of all, let's look at the autocorrelation of the subpologized sea surface temperatures in the fully coupled ocean and in the slab ocean. Clearly from this, you can see immediately that the time scales are different and that the fully coupled ocean has much more persistence. But then you can immediately say, okay, the slab is 50 meters deep. The full ocean can get to a depth of 700 meters or at least over 400 meters in some places in the subpologized in the winter. So it should have more persistence just because of that. So is that all that we see here? But in any case, there is already something that's emerging when you look at the time behavior. So the next thing that we did is we looked at the relation to the atmosphere, and I will return to that in the following slides. So what you see in those two diagrams is the lag correlation. So the horizontal, the x-axis is in years, because we are using annual data in all this study, and the y-axis is the level of the correlations. In this case, the upper diagram goes from -0.4, correlation of -0.4 to +0.4, and the lower diagram from -0.3 to +0.5. So it's not perfect. We should care about using the same ranges on the axis. But anyway, what you see here, so the way we define the NAO is we calculate the leading EOF of the sea level pressure, annual sea level pressure variability over the North Atlantic basin, slightly going east and west to capture the continents on both sides, and we calculate the leading EOF. The leading EOF comes out like that. It's actually a negative phase of the NAO. So what you're seeing here is a correlation between the negative phase of the NAO and the subpologized sea surface temperatures. So if we look at the bottom diagram is easier to understand. It shows that, and it's also, I should add, it's based on 5-year running means of both the atmosphere, the NAO index, and the ocean. So what you see in the bottom diagram is that with a slight lead of the, maybe I can grab an arrow here, a slight lead of the, maybe by 1 year or so, when you have a negative NAO, you get a warm subpolar gyre, which is what the behavior of the interaction we know of from looking at interannual variability in the observations. The correlation drops a little bit negative, but these are values that are slightly larger than 0.1. And the slab has about 1,000 years of data. In the coupled model, we see something quite different. We see that if we go back in time to 6 years before, when the NAO leads the ocean by 6 years, we see that the negative NAO is in a negative sign related to the SST. That means we have a positive NAO in this 6 years before the ocean reaches warm subpolar gyre conditions. So a positive NAO leads a warming in the subpolar gyre. The correlations are not very high, but they are significant because we have 1,800 years of data in this case. So that already begins to remind us things that we saw in idealized coupled model simulations that Martin Wiesbeck and Gerd Krumin read here at Lamont, and also people ran at Max Planck Institute at that time. Eden and Willebrand wrote about this. So I'll go back to that quickly at the end. So the way to understand it is that the forcing from the NAO triggers a gyre or inter-gyre interaction of some sort, or maybe deeper than that, including AMOC as well. But right now we don't really have full answers to that. So how do we demonstrate this a bit more clearly? So what we did is we went back to these 15-year differencing runs, and we identified 10 positive transitions and 10 negative transitions in the data. And this diagram just shows a composite of these periods in the data. So what you see is we did it in 5-year jumps in order to emphasize the transition. So from year 14 before the change from negative conditions to positive conditions are averaged together and are shown in the upper diagram here on the left. Then you see the next 5 years, the next 5 years, and then the transition itself is clearly obvious here when you transit from cold subpolar gyre to warm subpolar gyre, and then it persists a little bit longer. Part of the persistence in this case is imposed on the data by doing these 5-year running means. I'll say something about it at the end. So what does the atmosphere do at the same time in the fully coupled model? So we see here sort of like undefined perturbations leading to some sort of forming up a negative, I should always be careful about that, a positive NAO in year 0 to -4 to 0 before the transition, in the 5 years before the transition. And then after the transition, the positive NAO persists a little bit longer and then dissipates, and at the end we see a negative NAO coming up. So this confirms the lag correlation diagrams that I showed you before, that a positive NAO leads a transition from cold to warm in the subpolar gyre. And I should say, and I'm not going to show it for the sake of time, that the behavior is completely linear. If you look at negative transitions, you see exactly the opposite in both the ocean and in the atmosphere. And here is what the slab ocean is doing. Again, we do these 5-year averages before a transition and after on the right-hand side, and you can see that a transition really happens because that's how these diagrams are defined. This is how these composites are defined. But you see that the change between before and after is strongest, and that's why I marked it like that. The difference between negative and positive cases is strongest in the middle years. And if you look at the atmosphere at the same time, you see that the difference in the atmosphere is also strongest in the middle of these 5 years, in the middle of these 15 period of transition. So that clearly confirms that there is an immediate response, or quite immediate response of the ocean to the forcing from the atmosphere, heat flux mainly, and maybe, no, I don't think that even you can include Ekman here because the slab is not moving at all. So it's just heat flux response. Okay, so again, to demonstrate this thing, I use here a regression, a correlation between a index of the subpolar gyre, in other words, the average SST over the subpolar gyre, correlated with the atmospheric field above the Atlantic. So this is North America here, and Europe, and this is the Atlantic Ocean, and Greenland is here. So, and I'm organizing it such a way that what you see here is what happens when the NAO leads the subpolar gyre SST. And you see 10 years before the subpolar gyre, so this is based again on annual means average, smoothed out to emphasize a period of about 9 to 10 years. So 10 years before the peak warming in the subpolar gyre, the NAO is a positive NAO, and it continues like that and then dissipates after the transition of the SST to a warm phase. So a positive NAO leads a warm subpolar Atlantic. And to look at the ocean, so that I'm just as a reminder, I'm putting up the diagram here. And again, in the coupled ocean, if you then take the NAO as an index and you correlate the SST to the NAO, you see that hint of an emerging 10 years before the subpolar gyre reaches peak warming. You see a hint of a shift northward of the Gulf Stream, of the North Atlantic Current, which intensifies with time and eventually blows up into a full warm subpolar gyre beginning by 4 years before zero lag. Then finally, and just to show you that the NAO autocorrelation, even if it's smoothed in time to emphasize this sort of low-frequency interaction, loses its correlation after less than 6 years. So it's not the correlation of the NAO. There's no cycling in the correlation of the NAO that imposes this behavior on the correlation diagram that I showed you earlier. And just to remind you, here are the figures from KRUMIN et al. From 2001 that show this kind of a propagation of a warm anomaly from the subpolar gyre into the subtropical gyre, turning into a full-blown warm subtropical gyre I forget how many years it's shown here, but I think this is year 0 and this is year 5 or something like that. So it's a 5-year transition. So okay, so that's what the model that KRUMIN and VSpec used at the time is doing, and that's what the CESM is doing. Is there anything like that in the observations? So it turns out that I had some of these diagrams where I actually tried to see if the VSpec KRUMIN behavior appears in the observations. So what I'm showing here is SSTs in the subpolar gyre in black and in subtropical gyre in red. So I defined it according to these latitude-longitude limits, and I shift here the subtropical gyre 4 years ahead in such a case to maximize the correlation between these two curves. And down below here I show the numbers that the correlations are at 0 lag are really small, and at 4 years lag, when the subtropical gyre leads the subpolar gyre, you get a correlation of 0.4 without smoothing and 0.5 with a slight 1-to-1 binomial smoothing. So essentially, I didn't prepare a summary slide. I'm just going to say that what we are finding out is that the behavior in terms of the ocean response to the atmosphere is entirely different in the slab ocean and in the in the fully coupled ocean. Does it matter for climate? Does it matter? Well, it certainly matters for the ocean, but does it matter for the atmosphere? There is no clear evidence that that is like that, and we've always had trouble of finding an atmospheric response to changes in the ocean in the GCMs that have relatively coarse resolution and no deep stratosphere, for example, because some people claim that this is what's helping in getting a better response. So I think it's still an open question to look at. And there's also, of course, an interest, of course, to keep exploring what's happening in other models and what's happening in the deep ocean, and what's forcing the phenomenon. But in the end, this is not a really new result. It reminds us of work that was done in the early 2000s. So thank you.